Okay. So good evening, everyone. This is 576. So today I'm gonna discuss feed-forward neural networks and convolutional neural networks. So I just changed the setup a little bit so that I can actually have my writing on the notepad rather than on the board. Okay. Okay. So. Let's see a few things. Okay, so in terms of, I just wanted to see what the logistics were. So in terms of logistics, how many of you have not registered on the forum yet? Okay, there has to be some people who have not registered yet on the forum. Okay, so I got about 12 students who responded to the group formation. So people who have not yet formed groups for projects and assignments, you should talk to each other. There's actually a thread which is on which some folks have posted that they're looking for group mates. So you should join one of the groups. Okay. So the reason it's important is that two things. First is actually I'm trying to give you guys access. Okay, two things. First thing is assignment 1 is out anyway, so you want to kind of do it with your group rather than individually. Second thing is I will need your SSH public keys so that I can give you access to some machines with GPUs in them. Okay, it's not needed for assignment 1, but in general it will be useful if you kind of work on some deep learning projects, or not projects, but when we go through the course, you will need a computational resource which is different from your machine. So I need your SSH key. So I'll send you an information. I'll send information about this on the forum. So try to make groups pretty soon. Okay. What else? Okay. Another logistic question. How many of you did not set up Python yet? It's fine, you should speak up. Okay, everybody has Python on their machines? So no problems installing Python 3.6 or 3.7? Okay, so you can use any IDE you want, like PyCharms or like Visual Studio Code or something like that. So how many of you are seeing Python for the first time in this course? So you've not seen Python before, but you've seen other programming languages. A couple of you? Just two? Anybody else? I mean, you have to speak up. Otherwise, I'm going to jump forward and skip Python.
We have done a few basic online courses, like introduction to Python or something, but I haven't explicitly done anything.
Okay, that's fine. So here's the deal, right? If you don't speak up, I'm going to be very fast, and then you'll say I'm not able to understand what the lecturer is speaking, right? So it's important. I mean, this is an interesting occasion. There are only 30 odd of you, so let's put the brakes. Let's have discussion. Let's revisit some concepts which are incorrect, which you thought you're rusty on. Let's revisit them as we move forward. Okay, so let's see. What should I do? So let's see. So how many of you, okay, so here's the exotic part. You can actually run Python not only on your machine, you can run it on the server, for example, we'll see in the future. And you can actually access the kernel, the Python kernel through your web browser, even if you're not in front of the machine. Okay, so right now I have somehow set up so that this Python is not running on this Chromebook. It's actually running somewhere else. And I wanted to, so this is just I just cloned the GitHub repo for the course. the website. So let's go here. So you must have noticed on the syllabus page, I have kind of been revising a little bit about the names of what these links are. It's the same links. For example, so Python review is new. It's basically the basics that I'll go through in the next few minutes. But the second and the third link are essentially the same as before. One script is just generating this data set that we saw last time, and the other script is actually doing linear classification using the hand-derived backprop equations. Okay, so we'll go through the script actually very quickly now, and for today's lecture, there's also a couple of scripts. You can kind of try them out. Actually, I'm not innovating in terms of these scripts. These are actually well tested. For example, the second script is actually from PyTorch tutorial, but it's good for us to go through, walk through the script and see, what transformations, what is the workflow, right? From how's the script organized. So let's start with the basics. So let's see. Okay, so this is going to be, is it too blurry or is it visible? It's fine, right? Okay, so the first few minutes is going to be extreme basics. So people who already know Python can also chime in and help us out, help us go through this. So the base objects are, of course, variables. So there are a bunch of variables here, x, y, and z. And I'm just printing out a few things about these variables. The interesting thing is you can find the type of the variable, right? Here in this case, x is of type int and y is of type float. Okay, so there's a difference between these two, right? Integers and real numbers, essentially. And you can also see that x divided by z. Okay, so sometimes some programming languages have this issue. If you divide an integer by an integer, it will round to an integer. But here it's not the case, so it's 1.5 both times, so you're fine. And next, there is a few things that you might have seen in some other languages, like x plus equal to 1 just means x is equal to x plus 1 increment, right? And this just means y to the power 2. Okay, double star just means power. So you could have written a function called power, takes an argument and two arguments, y and something else, and then it gives you back y to the power that number. So in this case, it's 2, right? So y square. Professor, can you magnify the browser a bit? Okay. Okay. Yeah. Now I was just going through. So these are, I think last time we went through these cells, and some of you guys knew what these code cells were on Jupyter. So this is just a Jupyter interface or IPython interface previously. So you can run these, blocks by just inputting shift and enter. Okay. Actually, your assignments, I have suggested that you guys submit a script, a Python notebook like this. Okay. So I don't want any other information. I definitely don't need the data set because I know the data set for the assignment questions. And you can write your answer in this. There is you can write text blocks. Okay, so you can change the type of cell. I don't know which. Cell type. You can change it to, for example, markdown. It just is essentially text. You can just write down your answer there. Okay. Like, for example, this one is a text type, text field, actually, basic data types. Okay. So that's good. So variables, I'm not explicitly defining the types of the variables like some of the other languages, C++, for example. And you can also do multiple assignments. You'll see, this type of code pattern where assignments to variables are happening simultaneously multiple times. In JavaScript also you can do this. Okay. So A is assigned true and B is assigned false. In that line, in this third block, and have a string, which is just you can use single quotes or double quotes for the string. And here I'm just printing the two booleans and then the string. Okay, and then I'm also transforming the string. So string itself is an object which has a few functions, right? So you can do string.upper to get the capital case. Okay, it's 676 here. Okay, doesn't matter. So just simple statements, okay, just to get familiarized. And anyway, this script is there, so try to see, this is just a cheat sheet, and you probably will not need it after the first couple of hours. Okay. Next, interesting data types in this language are dictionary, list, and tuple, and set. Set, I guess, is the simplest thing. Set is just a collection of elements, right? Like 1, 2, and 3 is a set of numbers. But what if you had 1, 1, 2, and 3? That would be, there's a repetition of the number 1, right? So you can think of that as a list. Okay, there is an order relationship in the sense in the first entry of the list, then there's number 1. Second entry of the list, there's number 1 as well. Third entry, it's 2, and fourth entry, it's 3. Okay, so you can index a list. And a tuple is nothing but an immutable list. You can just think of it as an immutable list in the sense that you cannot change the entries of the tuple. Okay, it's like a list. In list, you can reassign, let's say, the third number to be something else. In a tuple, you cannot. Okay, and the last one is a dictionary. Sorry, that was okay. Last one is a dictionary, which I think I just do. Yeah, and it's tuple. So list and tuple are printed. We have printed it here, right? So I, D, and S are the list of characters, and a tuple of numbers is 5, 7, and 6. Okay, and I'm reassigning the same list, my list, with a different bunch of characters. And I can also do operations like appending to the list and extending the list with another list. Okay, so if I ran this, and now the first 3 entries have changed, and I've appended an entry 5, and I have extended the list with another list which had the entries 7 and 6, right? And then you can also index, like some of you who have seen MATLAB or R, you can also do indexing. So you can get a part of the list, right? So if you want just the first 2 elements of the list, then you use this notation :2, and not just the first 2 elements. If you want to assign the first assign something to the first 2 elements, you can do this in this way. Okay, I'm assigning A and A to the first 2 elements, and that's this first output. So I changed C, B to A and A. So that's the list. And then if I do a set of this list, then I'll get rid of the repeating elements. So it's like a unique operation in R. Some of you must have seen it in some other class. Okay, and so that's list and sets and tuples. Next is the notion of a dictionary. A dictionary is a key value pair essentially. So it's essentially like a dictionary. If you open a English dictionary, then you will have a word and its explanation, right? So think of that as a key, the word as a key, and the explanation as a value. I mean, instead of explanation, you could have arbitrary things. You could have images. You could have something else as a thing which the key which corresponds to that key. So here, as I said, tuple was immutable. So what was the value of the tuple here? 5, 7, and 6. Okay. Keys can only be immutables. Okay. So keys to the. Okay, I take it back. So I've made the tuple a key to this dictionary. Okay, one key is going to be my tuple, and it's going to correspond to a value, which is that string, advanced prediction models. Okay. You can also have other things. You can have numbers as keys. You can have strings as keys. So keys can be not everything. It's just a simple data types. Okay, and so these are the 2 keys. My tuple, which is 5, 6, and 7, or 5, 7, and 6, and the tuple for and the second key is the string 5, 7, and 2. So if I run this with shift and enter, so you can see that the key is the tuple for the first guy and the string for the second guy. Okay, this is going to be useful. For example, especially in text processing, you may have a bunch of text, and you have the words in the text, right? Let's think of English text. We want to not work with words, so you will map each word to a number. Okay, that's typically what's done, and we'll see it later on in the course. So you'll map it to a number. Just means that replace the word a, or replace the word the with some number, replace the word university with some number, and so on. Okay, And then what you may find is that some words are extremely rare. Okay, you want to drop such words. You drop such words, then your numbers are no more, there will be gaps in those numbers. Okay, so a dictionary is a nice way to not have a gap. So you can keep a dictionary which maps the word to the number, and you can have another dictionary which maps a number to the word. And when you construct those dictionaries, you ensure that there is no gaps between the numbers. Okay, it's just useful. You don't want gaps because, for example, maybe your classifier's output is the word itself. Then you don't want to have a classifier which corresponds to some words, but there is a gap in the number, and then it's predicting some other number. Okay, we'll see this issue later, but dictionaries are useful to at least keep track of which words correspond to which numbers and which numbers correspond to which words, and then you can work pretty much on the number side. Okay, forget about the words. That's that. And there's a simple for loop. You can print the entries of a list. Okay, each element of the list. You can also do something like I comma x in enumerate. Okay, where I is a variable here, and it's gonna tell me that the 0th entry, so it's 0 indexing here, 0th entry is A, and the 5th entry is 6. Okay, so there's also another interesting operation called zip, but we'll see that later. Okay, zip. If you have two lists of the same size, maybe 4 elements, 4 entries, you can kind of put them together so that each location has 2 entries now. Okay, zipping together 2 lists. Now, functions. So here is an example function which I think we saw last time when we were doing this backprop computation. So the function is defined this way. So first of all, I'm importing some packages here, math and numpy. Okay, I didn't short form it, but people generally use import numpy as np, okay, or import pandas as pd, right? So pandas is a really nice data processing package for Python, similar to I guess similar to tdverse maybe. So this is a function. So you just have to write def space the function name and the arguments for the function and what it will return. Okay. We'll also see in some scripts people use something called anonymous functions. Does anybody know what anonymous functions are? Yeah. So these are functions where you don't have to explicitly specify the name of the function. Okay. So it's not at this level, we don't need it, but we'll see in some scripts. For example, you may get some scripts from online where we're going through maybe transfer learning or something like that later, and we'll see that we'll use lambda functions. Okay. There are analogous concepts in JavaScript and maybe even C++. I don't know, but this is how you define a function. And I'm just evaluating the function at with a couple of inputs. The first input is just a scalar; it's just -20. Okay. The second input is actually a cast operation is happening. So the argument for the string that I highlighted there, the argument input is a list. It's a bunch of numbers, -1, 0, and 1, right? It's a list of 3 numbers. I'm casting it as a numpy array. So I'm changing its type to a numpy array. So what is a numpy array? Just think of it as a vector. Okay. You can have multi-dimensional arrays, which are essentially matrices, and we'll see tensors later on today. So I'm just casting the first list as an array, and then I'm passing it to Softmax. So what Softmax will do is that I haven't explicitly said whether it's going to operate on a single number or a vector. But if all operations, like for example, Softmax is using this math.e, which is the actual e, 2 point something, e to the power minus z, right? So it's an element-wise operation. So even if you pass a vector, it'll pick the first guy, apply the operation 1 by 1 plus e to the power minus z here. Pick the second guy, apply the same. Third guy, apply the same. Okay. So you can see that, for example, this Softmax function, which is essentially, I don't know why I'm calling it Softmax, is a sigmoid function. Okay. When you input 0, its value should be 1/2. Okay. So it's 1 by 1 plus e to the power 0. E to the power 0 is 1. So 1 by 2. Okay. So that's that. NumPy is going to be very important for us as we work through, especially deep learning. We work with matrices, essentially, or tensors. So NumPy and its, I guess, cousins in other packages like PyTorch and TensorFlow will be very useful. So definitely go through a NumPy tutorial, search for NumPy and go through a tutorial when you get a chance.
What if I use a normal list instead of what NumPy arrays?
Yeah, you don't. Yeah, in this example, you don't have to. You can. Oh, okay. We can try actually. I don't know. So there's many other things you may not know on the top of your head. You can just try it out. So let's see. Did I run this? What's happening? Okay. So okay, that was bad. Type error. So bad operator for, yeah, so there's some issue here. Okay, so you can't pass a list. It doesn't know. I mean, math. I think the math function doesn't know how to do e to the power. Yeah, to the power of some list. You cannot do that. So actually, I am quite bad at the keyboard shortcuts. You should look at the help and see what the keyboard shortcuts are. There's a bunch of them. Okay. It'll be very useful to actually look at function definitions. You can actually see the definitions and do the help that you do in, for example, in R. You can do it and do it here as well. Okay. So let's see, NumPy. So we just saw an example of a NumPy array. So A is now, so there I use as array. You don't really need to, I mean, there's a difference. We need to look at the function definition. But here I'm just assigning the variable A. Where is it? Assigning the variable A to be equal to this NumPy array, which has 3 elements, a 3-dimensional vector essentially, and I'm printing the printing a few things. A itself, then the type of A. It should return as some sort of a NumPy array, and the shape of A. If it's a vector, then it's going to be something like this. So 3 comma nothing else, and A dot data type is just the type of entries in the NumPy array. Okay. So you can change this to other things like float and so on. Okay. If the inputs already had something like 1.1, then this would be float. Okay. And so I created another NumPy array. In this case, the B is actually a matrix. Okay. It has 2 rows, essentially. So you can see that it's the same class, but it has 2 rows. So it's 2 rows and 3 columns. Okay, a slightly different response. So you need to pay attention whenever you're seeing this. If you have vectors, you don't get the second coordinate, so you can see whether the second coordinate was a null type or a none type here. Okay, none is the keyword for Python, and know what's happening with the matrix with the NumPy array. Okay, so with arrays you can do array indexing. So the first one is saying, okay, I have the B matrix, so let me pick the first row onwards and up to the second column. Okay, so indexing is from 0 for both rows and columns. So 1 colon just means pick the first 0th row is 0th row, first row is the first row onwards, but B only has 2 rows, so it's just the second row, and pick the columns from 0 to something means 0, 1, 2. I mean, here it's not going to be 0 to something means just one number before that. Okay, so 0 and 1. Okay, the first 2 columns. First 2 columns is last row. That's the indexing. These are not simple examples. I've crammed in a few things into each line, but that's what's happening here. So you can basically, the question is, if you have a matrix and you want to get a few rows and a few columns, you can easily subset, okay, and get a smaller matrix or a vector, for example. Okay. Any questions? Yeah. And then, okay. So, okay, I guess this block was trying to illustrate the difference between this indexing here, where I had a 1 colon, and without the colon here. So without the colon, it will give me actually just a one-dimensional array, and so the shape of it would be 2 comma nothing, whereas the first indexing keeps the matrix shape. Okay, so there is one row and whatever, 2 numbers, 2 columns, whereas the second one doesn't have a notion of a row anymore. It just has 2 entries, so it's like a vector. Okay, there's a slight difference between these two. So I'm just pointing this out because sometimes you'll run into these errors, and it's a good place to figure this out. Okay. You can also do indexing. So how many of you are actually familiar with R? Okay, so you must have seen these types of indexing, right? At least for data frames, you know how to condition. You know, like for example, a column is greater than some constant or is equal to, belongs to some, take some values and so on. So here it's a similar idea. You can actually, when b greater than 2, essentially just means it's comparing every entry of the B matrix. It's a 2 rows and 3 columns matrix, right? It's checking every entry is greater than 2 or not. If it's greater than 2, true. If it's not, false. Okay, that's it. So that's why only the last column had 3 and 3, and so that's why 3 is greater than 2, and that's why there are trues there. Okay. Yeah, and here I guess the first one is just comparing b greater than 2, and the second one is indexing. So b greater than 2 will give me the same sized matrix, so two rows and 3 columns, but it will have 2 trues, right, in the last column. So b of that would give me just those entries. Okay, it's like logical indexing, I guess. Yeah. And yeah, next I'm just trying to illustrate. Here we are trying to illustrate what is a product, right? How do we get a matrix vector product, and how do we get an element-wise product? Okay, and the first way where you think of x as a matrix and y as a matrix, if you just do x star y, it only multiplies elements together, and that's it. Okay, it's element-wise product of the 2 matrices. In this case, these 2 matrices. So 1 times 3, 2 times 4, 1 times 1, and 1 times 1. Okay, whereas if you do, okay, so here I've not done a, okay, here I've done a dot product between the matrix and the vector. Okay, so you have to use x dot z. Okay, so in notation we just write a times x. Okay, but here we have to use a matrix dot operation would be there for that matrix because it's a numpy array, bracket the vector. Okay, and you also have some additional functions like functions like sum. A dot sum would sum all the entries of the, sorry, x dot sum would sum all the entries of that matrix, and x dot t would be the transpose of that matrix. Okay. Last one is just a simple example of how to work with images. So here there's some package called image.io which I installed, and here I'm just trying to, so this is just the image from the class website. So I just said, okay, let's read that image and then plot it. So for plotting, I'm using matplotlib. So it's a plotting package. It's pretty standard. So for example, this would be a standard template. So you don't have to really, you can delve deeper into it, but it's like import matplotlib.pyplot as something, and then that something.subplot. Maybe you want to have, these arguments don't, you can remove those arguments actually, it doesn't matter. And then plot.imshow of, for example, here I'm converting the image. So imRead, so we can look at these functions and see what their what the return type is. I'm again typecasting here from whatever the argument was, img, to some different numbers, so that I can use imshow to plot it. imshow to actually generate the figure, and then the next sentence is to show the figure in this notebook. Okay, so very quick overview of Python, but I would suggest, especially people who are coming from R, you will not find it difficult. Just get familiarized with these. It will make, and this is a good time to familiarize because we'll get into some details of deep learning later, and so we'll not have time to look at these. Okay. How many of you were able to run the linear classifier from last time? You're able to run, so at least on a notebook. So the Jupyter script was given, right? So Anybody faced issues with running this script, running this notebook? No issues. Actually, I only see few people have run it. So remaining people, we should definitely do it after this class. Okay. What I wanted to kind of actually, yeah. So this is what we saw last time, that linear classification would give us this. So a few details I kind of skipped over last time. Sorry. Okay, so last time I think I mentioned that the objective function was actually least squares loss. So the difference between y's and y hats, right? Which and y hats were just wx plus b basically. So let me write it down actually. Yeah.
Quick question: should we install two kernels of Python 2.7 and kernels of Python 3?
No, it's not needed.
So Python 3 is okay?
Yeah.
So for all packages of the deep learning?
Yeah. So we'll mostly work with Python 3. So it says on the top here. So I think if you install, I think you can change here. So there's this notion of virtual environments, and you can have multiple Python programs running simultaneously. You can switch between them and all that. It's worth exploring though. Okay. Where is this? Use the. So what's the best way to do this? Okay, let's see. Okay, so last time I said, okay, think of a classifier which is like wx plus b. Okay, where x for us, remember w was actually in that example. I think we have three classes, right? So w is 3, and data was 2-dimensional, so that's why I was plotting it. So the second dimension of w is going to be 2. X is any of the data points that I have. It's going to be 2 cross 1, right? And my bias was again 3 cross 1. Okay, so I had 3 classes, and I was saying that okay, I'm gonna, given the input feature vector, I'm gonna do a transformation like this. It's a linear transformation because I'm just multiplying with it's actually an affine transformation to be technically correct. So I do this transformation, so I get 3 numbers. Okay, so I'm calling it. I'll get 3 numbers. So this is S 3 cross 1. The subscript is just representing that it's the dimensionality of this object. So that S is what I'm calling as a score vector. Okay, it scores, and these scores can be anything, right? If I put if I choose a W which has entries which are both positive and negative, then the score itself can be, for example, positive or negative, right? For example, let's say I pick a W matrix. This is -1, -2, -3, 1, 4, and -5, and maybe some X is there, right? Then let's say X's are positive, for example, then you can see that the first entry definitely is going to be a negative number, right? So let's say X is 1, 1, then the first entry is going to be -3 of the score vector, right? Do you agree? So I'm just saying that the first entry, for example, is -3. The second entry is going to be, you can just do this, so it's -2, and the last entry is going to be, what is this? 5. Okay, it's going to be -1, right? I'm just saying that these scores can be negative, and so what people do is they transform these scores so that they are numbers between 0 to 1, and they also sum up to 1. Okay, so this is just this is a particular way of you looking at. So what I'm describing right now is just a multi-class logistic regression, but I'm just not alluding it to things that you have seen in the past. Okay, so what I'm going to do is I'm going to make these scores between 0 to 1 by doing this following transformation. For given S as an input, I'm going to do either for S1. S1 represents the first coordinate, first entry in that vector divided by e to the power s1 plus e to the power s2 plus e to the power s3. Okay, and the second entry is going to be very similar, e to the power s2 divided by the denominator and e to the power s3 divided by the denominator. Okay, where the denominator is this guy. Okay, so this transformation ensures two things. One is each of the entry is now positive because e to the power a negative number is still positive. Okay, e to the power minus infinity is 0. Okay, e to the power 0 is 1 and e to the power bigger numbers is even bigger. Second thing it ensures is that the sum of the entries is 1. Okay, you can see that, right? So denominator is the same and the numerators add up to the denominator, right? So that's one transformation. And then what I'm going to do is so I want to compare. So through this transformation, what I did is I got 3 scores or transform scores, which are essentially trying to predict whether X is in the first class or the second class or the third class, whether it's in the yellow class, red class, or the green class, for example. Okay, or it's not predicting. Given a choice of W and B, those are the 3 numbers being produced, and I transformed it. Now I want to ensure that whatever numbers are being produced, maybe the data point X is actually of the red type. Okay, then I want to, let's say the red type is, so there's red, yellow, and what was the other color? I don't know, green. Okay, so let's say I'm going to one-hot encode it as red being the first coordinate being 1, and yellow being the second coordinate being 1, and the green being the third coordinate being 1. Okay, this is just called one-hot encoding. It's just a way to represent qualitative things into a representation, numerical representation, right? So let's say this particular X here, which was 1, 1 here, belongs to the red type, red class. Then I want these scores to be, I want to pick W. So essentially I'm going to adjust W's, right? Those are the parameters of my model. I'm going to adjust them such that I'm going to get these numbers close to these numbers essentially. So this is what I know from my training data, and this is what I've computed for a given W, and I want to kind of change W such that these numbers are close to this. Okay, and I will not just use, so I will not use this vector minus this vector square. I could do that, but what I'll do is instead just pick the so let me say another thing. So this first entry is actually the probability of Y is equal to red guy given X. Okay, so that's what I'm gonna think of it as. The first entry is just saying that what is the probability that given this X, what is the probability that the Y corresponding to the X is red. Okay, second entry is going to be probability that this output is equal to, let's say, yellow given this vector X, and what is the probability that the third guy is the Y is equal to green given this X. Okay, and these are probabilities because these numbers only go from between 0 to 1. Okay, they sum up to 1 and they're positive, so they can only be between 0 and 1. And the loss function, so last time I think I said we were kind of motivated by least squares loss, the usual Y minus W transpose X or something, beta transpose X square, right? So here I'm going to use a different loss. I'm going to say, so whatever data I have, so data is xi, yi, right? This set, actually not a set, but a list from I is equal to 1 to maybe 100. Maybe I have 100 data points. Actually in the script there's 300. Actually, let's say 300. Okay, there are 300 observations, 300 points, 100 in the first class, 100 in the second class, 100 in the third class. Okay, so given this and a given choice of W and B is a particular model, right? So I want to score this model. That's what a loss function has to do. So the way I'm going to score it is to do it this way. I'm going to write the probability of Y is equal to red given X. Okay. Actually, let's say yi is equal to red given xi. That I can compute, right? For any given W comma B, and for any of those data points I can compute this, right? I'm gonna do I want to maximize this number actually, so I want to maximize this over W and B. Okay. So I want to somehow like the yi need not be red. Okay. Then I don't care about that part. So what I want to do is so what is that? So let's call this, okay, this is already, yeah. So yi1, yi2, and yi3. Okay. So it's just the ith observations, 3 numbers. Maybe the first coordinate is 1, which means it is in red. Second coordinate is 0, it's not red, and third coordinate is also 0, it's not red, right? So I'm going to use instead of saying this, I can use yi1 to the power yi1. Okay, I can just multiply these guys actually. Actually, no, let's drop it. So yeah, actually I can, yeah. So probability of yi is equal to, what's the second guy, yellow, right? Given xi, yi2, because the second guy is encoding. So why am I multiplying it this way is just to show you that, okay, for the ith observation, if it is red, then this term is anyway, something power 0 is not relevant anymore, it's 1. And similarly, I can multiply with probability of yi is equal to green given xi or yi2. Okay. So this is essentially saying that for the ith observation, pick the term which actually belongs to that class and maximize this guy. Okay. So for the ith observation, only one of these terms is going to be relevant because only one of the yi's is going to be 1 and the other two yi's is going to be 0. So 2 of the terms will be 1 here and only one term remains, and I just want to maximize that number subject to w comma b. And people, instead of doing that, they maximize the log as well. Okay, log of this thing. Okay, so this is a very weird way of defining the objective function, but this essentially is the logistic loss. This is essentially the cross entropy loss function. Okay, it's called the cross entropy loss function or the multiclass logistic loss function. It's the same name. So what does it? Yeah. So in terms of that script, so here in this line, I'm doing the given a current w and b, I'm multiplying it with the data matrix here. Okay, you can use np dot or x dot. Whatever w is the same type of operation, same operation. So this gives me a bunch of scores. Actually, it turns out the scores are three scores per observation. My x data matrix actually is 300 cross 2. Okay, two features, but 300 observations. So the score is actually is a concatenation of all the scores for every observation. So that's why it's going to also be 300 dimensional, but you'll have 3 scores. Okay, and you only want to pick, so you only want to pick that score which actually has a yi is equal to 1. Okay, so if it is a red class, then you just want to know whether probability of yi is equal to red given x, was that number high or not. Okay, that's what you want to maximize. Actually, did I write maximize there? Or you want to minimize the opposite of that. Yeah, I wrote maximize. So maximize this. Let's say yi is let's say in this case yi1, which corresponds to red, is 1. So these two things are irrelevant. And then for this guy, I want to maximize the. This is called the likelihood function as well. Okay, this term is called the likelihood. Likelihoods are just conditional probabilities. So this is a conditional probability of y given x. Okay, that's just you can, and sometimes you can call it a likelihood as well. And I'm just maximizing the likelihood. In particular, I'm maximizing the log likelihood. Okay, so it's just maximum likelihood objective here. Okay, and if you want to maximize the term, you can also minimize the negative of the term, and that's the loss function. Okay, so loss function, you think of, you want to minimize it. Here I'm talking about likelihood and maximizing the likelihood, and so you can just put a negative sign. in front and think of it as minimizing. Okay, so minimization over w comma b of minus of this log of this probability or this likelihood. Okay, the likelihood corresponding to the y where it is actually true. Okay, that's the loss function. That's a cross entropy loss function. Or I mean, I don't know. So have people seen cross entropy loss function before? Okay, some of you have seen. So if you do this, then it essentially is the same as writing. So this objective, the same as writing sum over y little I. Now I'm using capital Y to represent the capital Y in our case is 3. It's a generic variable, has 3 coordinates. So sum over I is equal to 1 to 3. Okay, of log of the my prediction. So okay, what is this? Let's call it pi. Did I use any number? So pi is nothing but the e to the power scores si divided by sum over I is equal to 1 to 3 of e to the power sj. Okay, let's use j. The transformation. Given the score, I do this transformation. I'm just calling it p's, and this is the cross entropy loss function. Why cross entropy is because there's a thing called entropy that we may encounter potentially later. So that has a similar form. It's a sum over bunch of log of probabilities. Okay. So it's nothing. I mean, it's the same explanation. I'm just saying. I mean, if people have seen this form, it's the same. And there's a negative sign, and you want to minimize the cross entropy loss. This is a cross entropy loss. Okay. So this is a loss that we are trying to minimize in that script, right? And so we have to do, so in this script what's happening is we are doing a backprop operation. It has this log of something. Yeah, it has this as a final objective. This thing is a function of scores. Scores is a function of w's. Remember, you can think of it as a computational graph. Like given an x is fixed anyway. Given a w, think of w getting multiplied with x's. So there's some w times x. There's some additions and multiplications happening. You get a scores. Scores are getting transformed. You get 3 scores. They're getting transformed. All 3 are entering 3 different things and getting transformed this way. And then each one is entering into this term and getting log transformed, and then they're getting added up. Okay, that's actually that's the computational graph. And then you can think of doing backprop computation, the local computation that we saw, chain rule last time, and you'll that'll get you closer to the script. Okay, in the script, what's happening is 2 things are happening. One is that the manual backprop computation. In addition to that, they're also doing vectorized computation. So they're not looking at each data entry, so each observation xi, yi, or the 10th observation and 10th label. They're looking at all the observations together. Okay, so that's why there's a little bit of matrix computations going on. Okay, that's second degree of complexity. But once you understand, this is the loss, you know how to derive backprop by hand, then you'll be more comfortable with what's happening in the script. Okay. Any questions regarding this? Okay. What was my schedule? Okay, 6. Okay. So what we'll do now is jump over to, again, now what we're going to do is we'll try to understand, get into deep neural, get into neural networks. So today we're going to look at feedforward networks. Okay. Any questions, about the script? We're going to now go back to non-coding. We'll just get back to the basics. Okay. Okay. So let's see. Okay. So we So actually there was a reason why we went through the multi-class logistic regression example. So that linear classifier script essentially is implementing a multi-class logistic regression. So before I get into neural networks, so some people must have seen logistic regression before. How many of you have seen logistic regression before? Especially the 2-class version. Okay, 2-class version is slightly different. Okay, remember in the 3-class version there is a W matrix which has 3 scores which is being output. That's what you saw in the previous page, right? If you're thinking of a 2-class logistic regression, it's redundant to have 2 scores. Okay, because the scores add up to 1. I mean, not the scores, but the transformed versions of the scores, these probabilities add up to 1. So if you know one number, you know the other number. Okay, so for 2-class logistic regression, you might have seen using just a vector, okay, as the model, as a part of the model, just like a beta transpose X or something, okay, rather than a matrix which is 2 rows and whatever number of features, in this case 2 features. Okay, so that's just caveat, and if you're confused about it, let's talk right after the class or during the break. Okay. Okay. So the reason why we went through the logistic regression, multi-class logistic regression, is that a feed-forward neural network is essentially the same object, but with some additional computations in between. Okay, if you think of the computational graph. So let's see what that is. So the function for multi-class logistic regression was had 2, I guess, parameter sets, W matrix and the bias vector, right? Which is, for example, 3x2 and 3x1. Now, instead of that, so this was logistic regression. Instead of that, feed-forward network, for example, with one hidden layer would be, so this was just W times X plus B. Okay, that's the, so what is this function? What is this function doing? It's just outputting those scores, SIs. Okay, just think of what is getting output as a score, and this is the function. And what we're going to do is change that function, only change the function, keep the loss function the same. It's just logistic, the cross entropy loss as before, and change the function. So W1, B1, W2, B2. So this is the smallest example where I'll now have 2 matrices. I'm just going to index them as W subscript 1, W subscript 2. Okay, and I'm going to choose a particular function, and we'll discuss a little bit more in detail of why that function. So the function is going to be W2 times max of 0, W1 times X plus B1 plus B2. Okay. So what is happening? If you think of in terms of a computational graph, this is the same as before. So I'm just doing Wx plus B. Okay, I got a bunch of numbers. Okay, those are actually called, there's a terminology, I will just introduce it right now. Those are called activations. Actually, pre-activations, let's say. And then I'm passing through these, I have, let's say I have, let's pick something concrete. So let's say W is 5x2. Okay, 2 is just the features, X is 2-dimensional, so the number of columns of W1 at least, has to be 2. And I'm going to just pick the number of rows of W to be 5, some number. Okay, and so B1 is also going to be 5x1, right? 5-dimensional vector. If I compute this W1 times X plus B1, I will get a vector, right, which is 5-dimensional, and that's gonna be essentially, 5 numbers, and I'm going to apply a max of 0, those 5 numbers, which essentially is an element-wise operation. So I'm going to do a max of the first number and 0, and if it's negative, I'm just going to pick the 0. Okay, and max of the second number and 0. If it is positive, I'll just retain the number. Okay, so that's what the second, there's just a way of writing it. It's saying if the second argument is a vector, just do element-wise operation. Okay, max of 0 and that. That's the operation. The output, I'm going to call it as the activations. I guess activation vector, it's a 5-dimensional vector. Each entry, think of it as an activation. Okay, so that's activations. and then it's going to be, so this is 5 cross 1, let's say, right? Then my W2, I have 3 classes. In my example, there were 3 classes, right? So W2, the number of columns, number of rows has to be 3, because I want to output essentially 3 score vectors. So it's 3 score values, right? One score for red, 1 score for yellow, 1 score for green, let's say. And its input, it's getting hit by a vector which is 5-dimensional, right? The intermediate computation is max of something and something. So this matrix is going to be 3 cross 5. Okay, so 5 is something which is relating the number of rows of the first matrix and the number of columns of the second matrix. That's fine. Okay, just so that the numbers work out and things are not incorrectly sized. Okay, so this intermediate thing is a computation of essentially what's called the hidden layer. Okay. And this 5 that I was alluding to is called the is just the number of hidden nodes. Oh my god. So that's the number of hidden nodes. Yeah.
Can you repeat the 5 cross 2 thing? I didn't get that. W1. How did it?
Oh, sorry, it was not W1. Oh, I just chose 5 arbitrarily. So you could have chosen 10 or 50 or 100. Okay. So I said, we need to somehow work with the input. Input is 2-dimensional. Think of our example. That's a running example. It is 2-dimensional. I am just transforming it into a higher dimensional vector. Okay. To 5 numbers or 10 numbers. And then I'm saying I need to anyway produce only 3 scores. So I anyway have to go back to 3 numbers. So that's why W2 is 3 cross whatever numbers I choose. So this 5 and this 5, it can be anything else. Okay, that's the number of hidden nodes. You can choose to be any number. Okay, one such operation like this is essentially called a hidden layer in the neural network terminology. Okay, what do I mean by one such operation? We'll see multiple such operations later on. Okay, just to kind of give a prelude to the future. So this is it. This is a one hidden layer feed-forward neural network. Okay. So if you're really coming from a non-neural network background, you say, okay, this is just a function. Like, what's the big deal, right? It's just a function with a couple of matrices as parameters and a couple of vectors as parameters. So there's no notion of neurons, layers, anything like that if you just write it as a function. But this additional terminology is just for us to kind of reason about it in a conceptual way. It's like let's just call this thing, the circle thing, as the computation of the hidden layer, and let's just call the next computation as it's something that computes the scores. Okay, that's all. So it's just terminology, and hidden because this computation is not really interfacing with the outputs. Scores are the ones which are getting scored actually by the loss function, and it is interfacing to inputs through x, but the intermediate computation is something that I arbitrarily chose. I imagined, okay, there's going to be 5-dimensional vector there instead of 10-dimensional or 100-dimensional vector. So it's something that you choose. It's not really it's not a data point, so that's why it's hidden. Okay, we just call it hidden. And so why did we choose max of 0 comma some number? I'm going to use z to represent some number. So this is just a function which was part of that definition right before. So it's a function which essentially is like this. So think of z on the x-axis, then the evaluation of the function is zeros all the way on this side. So let's say z is -3, then it's going to be evaluated to 0. If z is 4, then it's going to be evaluating to 4. Okay, that's it. That's this function. It's a non-linear function. Okay, and in fact you can choose many different non-linearities. So why this particular function? You can use any other operation there. People have used operations like so this is actually called ReLU. Okay, it's just again an acronym. You're giving names to things just to kind of have more intuition in this function space. So what is ReLU? ReLU is just rectified linear unit. Rectification is something that people in electrical engineering might have seen. Like you have AC signals, you kind of rectify to get DC, for example. So here, rectification just means that you're chopping off the negative part to, you're thresholding it to 0, and the positive part just stays as it is. So it's a linear unit, but the negative part is getting pushed up to 0. Yeah.
Why do we need a non-linear function?
Why do we need a nonlinear function? So that's the question. So let's say we don't have, so nonlinear function, so pictorial is essentially this, right? So what would be a linear function, right? Remember we had some slight ambiguity between linearity and affine functions, but okay, the difference between linear and affine functions is you should see the refresher on linear algebra, but linear function is something that in that parlance it goes through 0, okay, and affine function is something which can go anywhere, okay. So it's like this with an intercept which is non-zero, okay. So why do we need a nonlinear function is because if we just use a linear function, there's only one choice, okay, with one dimensions. You can change the slope, right? You can make the slope instead of 1, you can make it so what's an example function? F of x, f of z, let's say, is equal to 1/2 times z, okay. It's a linear function, goes to 0 when z is 0, and it has a slope of 1/2, okay. I could have chosen something else, it doesn't matter. If I use this function, let's use that function actually. So we had w2 times that function, so 1/2 times its input, right? So what was its input? w1x plus b1 plus b2, right? That's the function. Instead of, all I did was change this to instead of max of 0 comma something, I just made it 1/2 times the input, okay. That's what it is. The input is a vector, but you can think of it as acting element wise, right? It's this is a, remember we chose the number of hidden nodes to be 5, so this internal part was 5-dimensional, right? 5-dimensional vector, 5 numbers, and I'm just applying it to, I'm just multiplying it with 1/2, right? That's a linear function, and then I'm just multiplying it with, again, let's say 3 cross 5 dimensional matrix here, and this is 3 cross 1. So if you do this multiplication, you will see that it's just w2 times 1/2 w2 times w1, right, x, plus w2 times b1, right? I'm expanding the bracket there, plus b2, right? So this whole thing I can just think of it as another bias vector, and this whole thing I can think of it as another matrix, maybe w3, let's call this b3. So it's just w3 times x plus b3, okay. The 1/2, instead of 1/2 you could have chosen anything, it's the same, okay. So if you don't put nonlinear functions, you will get the same. It's as good as saying I'm doing this logistic regression, okay. That's essentially what it is. Is this clear what I said? Okay. So okay, where was I? Yeah, there are many other nonlinear functions. One popular one is what we've already seen, so sigmoid. Typically they use the notation sigma of z, which is 1/1 plus e to the power minus z, okay. So this is a nonlinearity that you can also use. How does this nonlinearity look like? It's basically going to 0. Actually this is 1/2, okay. It's going to 1 and it's going to 0 as z varies, okay. So when z is like really large, you can see that 1/1 plus something, when z is really large, like 100, e to the power minus 100 is kind of insignificant, so it's 1/1, so it's 1. And similarly, similar reasoning on the other side, e to the power minus z, when z is a highly negative number, is a huge number in the denominator, so you will get a 1 by some huge number is essentially something which is 0, okay. So this is another nonlinearity that you can use, okay. So there are many others that you'll see in the slides, but let's not worry about it. So this is just a way to kind of define a neural network, a feed-forward neural network. Okay.
So what are the parameters in choice of this activation function? So what parameters are important to choose an activation function that leads to a good
Yeah.
prediction?
So how do you choose between these non-linearities, right? Or essentially, they are also called the activation functions, as he was pointing out. So the choice of the activation function, the choice of the number of hidden nodes, the choice of number of hidden layers that we'll get to later, all those choices are pretty much data driven in the sense that it depends on the application, depends on the domain knowledge. Yeah. So there's no so there are in some engineering best practices like the ReLU one that we showed in the previous slide, previous page, seems to be pretty good. So it's like a default that you'll use in many of the packages in this course. Okay. Okay. So let's see. That's nonlinearities. Okay. Some nonlinearities are also have this idea of like a saturation, but we'll see when we get there. So saturation just means that so you're training, we are trying to find the best W comma B pairs, right? I mean, that's what, gradient descent essentially that we covered last time. We're trying to kind of get the gradient with respect to W, gradient with respect to B, kind of change them by multiplying with the learning rate of the negative gradient, part of it, right? So sometimes what happens is at certain operating region, which means that at certain W comma B values, it turns out that the evaluation of this, these types of nonlinearities will be on this edge or this edge. Okay, that means that even if because the evaluations are on these extremes, even if think of it as I'm changing the W, the evaluations are still the same. Okay, that means that you're somehow kind of stuck. Things have saturated too. So this is the word they use. Things have saturated. Gradients have saturated. Just means that you are in the W comma B regimes, which are kind of extremely bad. It's very difficult to move them away because, for example, Z greater than 100 all the way to infinity, millions, it's almost 1 essentially. It won't change the number. Okay, so whether you choose a W with, W has entries like 100, 100, 100, 100 or million, it's almost going to be the same. So you can't really figure out, you want to do gradient descent, but you can't really do much, okay, because your gradients have no information essentially. Anyway, so that's a very high level explanation of.
So with this activation function, aren't the function non-convex? Then how?
Oh, this function is non-convex. So convexity just yeah.
Backpropagation for, let's say
how do we backpropagate? So okay, so his question is this, at least for example, the sigmoid is non-convex. Okay, non-convex just means it's a function which has inflection. So it's a function where I can pick 2 points, in particular, for example, these two, and it cuts the function some way. Okay, so convex function is, think of it as like parabolas, where if I pick any 2 points, I cannot cut the function. Okay, that's essentially what a convex function is, and sigmoid is a non-convex function. Okay, so his question was, okay, this function looks non-convex. This is a non-linear function, right? How do you do backpropagation on this non-convex function, right? So that's the question, and the answer is, first of all, you can do backpropagation on any function, which is as long as it's continuous, so that you can take the derivatives. Okay, whether it is convex or not doesn't matter. You can compute, do the chain rule as long as you can compute the derivatives and pass the gradients along. Okay, because this function is this sigmoid is non-convex, it turns out that the loss function, the final loss function, remember, minus log of what I showed, the loss function, if you write it as a parameter, it's parameterized with W1, W2, B1, B2. This guy is also going to be non-convex. Okay, it's definitely not going to be linear. Remember, we just introduced non-linearity, so the loss function is not going to be something nice. Okay, for example, imagine the least squares loss, right? Think of linear regression loss. Linear regression loss, actually, you can intuitively think of it as like something like a ball shape. That's linear regression. That's the nicest case where you can actually do gradient descent and get to the bottom. Okay. Even for this logistic regression, the script that I gave you, no matter how you kind of do the gradients, I guess reasonable gradients, right? You will get to the bottom. You will get to the same W matrix and the B matrix. Okay, in that script. But the moment you have these types of nonlinearities, the ReLU nonlinearity or the sigmoid nonlinearity, it's not clear if you do gradient descent you will get to the same bottom because there is no notion of same bottom. It's like something like this. Okay, if just to pictorially represent the loss function. First of all, these are all lots of numbers, so you can't, loss function is not a one-dimensional function. First of all, right? For example, how many dimensions are there? 3 times what is this? 5 times 2, 3 times 5, 5 times, I guess. Okay, 5 times 1 and 3 times 1. Okay, these many parameters are there. You can't really imagine how many parameters are there, but as a function of these parameters, there's a surface, loss surface, right? I'm just kind of pictorially representing as a one-dimensional function with some, and I'm just representing that this function is highly non-linear and also not convex. Okay, so you do gradient descent, you may if you start from here, you may get here. If you start from here, you may get here. Okay, so there is issues like this, and this is essentially the issue with deep learning. You have non-linearities, which may or may not be convex, but the moment you introduce non-linearities, the final loss function is not a nice ball-shaped function. Okay, which is the case for linear regression, and so you will invent lots of techniques for doing all sorts of gradient descent variations, and hope that you get to a good, some sort of local minima, essentially. Is that clear? Okay. So, where was I? Okay. Yeah. So now I think in the next, we'll take a break, and before that, I just wanted to quickly run through, a Python script which has this one hidden layer feed-forward neural network, which is shared, I think. Which one? Yeah. So it's essentially the same classifier. Okay, let's see. Okay, I don't know if this works, but let's see, run. This doesn't work. So this was the data, right? So this is the 300 points that we had from the previous thing, and now our model has the same thing that what we discussed. Instead of W1, W2, I think we just use WB and W2, B2. Okay, and we also choose H here. H we just chose to be 100. I mean, in my running example, it was 5, but we can change it. Okay, and in fact, in your assignment, you will see, you can try changing this and see what's happening with your model. Okay. Did I run this? Let's say this. And then it's the same loop, except the loss part is the same, but there is a couple of hand-derived backdrop equations going on. It's very similar to before. Okay, and this is the last part that we saw even in the previous class. You have a negative step size, so W plus equal to something just means that W new value is going to be previous value, which is W itself, minus step size, which is the learning rate, another name for learning rate, just a nomenclature, times the gradient of loss with respect to W. That's what's captured in DW. Okay, so this is a matrix equation actually, because W is a matrix. Okay, so you run this. Okay, I don't know, run this. So here I'm just printing out some loss, the loss, the negative, the cross entropy loss value. Okay, but that itself we don't really care about it. We care about actually the 0-1 loss. I mean, not the 0-1 loss, so the classification loss. Okay, whether it was classified or misclassified. If it's misclassified, give a point, give a point to it, and if it's not misclassified, keep it 0. Then you can kind of look at, you want to be close to 0, you're not. That's essentially what we want, and that's what we're doing here. What happened? Yeah, so it says, I mean, it's really not test data because I'm using X test is equal to training data, so that's not correct. In your assignment, you'll do something different, by the way. And then this is the plot. Okay. So this is the choice. You just use the nonlinearity, same nonlinearity, max of 0 comma something. I mean, of course, we use now more numbers, right? Initially, the W matrix was just a 3x2 matrix, 3 classes and 2 for the 2 features. So essentially 6 numbers plus the bias. Here we have the hidden H is 100. So already, if you pick any of the matrices, it has 100 times. For example, the first matrix is 100 times 2, already 200 numbers. So it's a very, lot of numbers, lot of parameters. Okay, and because of nonlinearity, we can get really high classification accuracy. Okay, so let's take a break for till 7:30 and resume. Okay. So somebody during the break asked a question of what is where is the pictorial diagram for the network itself. I kind of skipped it because we will revisit this again. Pretty soon when we directly jump to convolutional neural networks. Okay, but this is the pictorial diagram. So what is happening here? We have the 2-dimensional data, right? X1 and X2. Let's say the first 2 coordinates, where I've used superscript to represent the index of the coordinate. So like a generic feature vector. The first coordinate is the top guy, and the second coordinate is the second guy. And W1, if you see below, W1 essentially corresponds to these edges. Okay, so we chose 5 as the number of hidden nodes. So I've just represent the nodes as these blobs, these circles, right? And so there's a linear transformation happening from X's to pre-activations, and then they get the pre-activations are getting operated on by the nonlinearity, max of 0 comma that number, and that gives me the output of those nodes. Okay, so these nodes here, think of this as like a max of 0 comma input, which is W1 11 times X1 plus W2 12 times X2. Okay, so why there's a lot of indexing going on. I just think of it as if I had X1 X. Oh, okay. Anyway, I'm just saying that if this is just the evaluation of the first row of your W times X. Okay, you had this operation, right? So the let's call the intermediate computation H. Okay, which is 5 cross 1. This is equal to max of 0 and W1 times X plus B1, right? So I'm just saying that think of the first row of this 5-dimensional vector. This final thing is 5-dimensional vector, which you operate on max of 0 comma something. Again, gives you a 5-dimensional vector. These are the activations. These are the pre-activations before passing through the non-linearity. And I'm just saying that I'm just representing this number as the first coordinate of H1. Okay. To make the point even second time, think of the W matrix as 5 cross 2. It has entry, it's a 10, 2, and some numbers. Okay, 4 times 2 numbers, and let's say X is just 1 cross 1, and plus B is let's say 1, 2, 3, 4, 5. Okay, that's B. So this is a pre-activation computation. So what I'm going to do is 10 plus 2, 10 times 1 plus 2 plus 1, 2 times 1 plus 1. That's my pre-activation. Just think of the first row, right? First row of the output would be just this. This I'm going to do a max of 0 comma this, which is going to be 13, right? It's a positive number anyway, it's fine. So that number is this shaded thing, okay? So that's why I'm saying that this number computation requires as inputs x1 and x2, right? Here 13 required the inputs 1 and 2. That's a first coordinate and second coordinate, right, of the input. And then I'm going to use the first row of the W1 matrix. The first row, typically, you have a matrix. The first element is W11, W superscript 11, let's say. First row, second element is W superscript 12. Just means the first row and the second column. I'm not using Python indexing in this, but first row is just 1. Okay, so those are the two things needed to get to this black guy, this H first coordinate, right? So that's why I just drew an edge with these guys sitting on the edge. Okay, so this times the first guy, this times the second guy. Add them up, add the bias as well, which I can maybe directly represent as B11, first coordinate of B1, and then add them together, take the max of 0, that number. That's the evaluation. That's the activations. And similarly, so that's, there are 5 such guys, 5 such activations I compute per observation. And then again, W2, to get one score here, you will add up these activations again with the second matrix's first row. Okay, the second matrix, remember W2 is a matrix which is 5 cross 2 in my running example, right? So just think of the first 3 cross 5. So it has 5 columns. So maybe, let's keep it simple: 1, 1, 2, 3, and 1. Okay, those are the 5 first row 5 numbers. Okay, that's what I'm representing here as W11, W12, W13, W14, W15. So subscript represents as a second matrix. Okay, I need to multiply that with these H, 5 numbers. Add them together, add a bias, again B2, 1, and that's my score. Okay, and then I'm actually going to do more, right? Remember from scores, I did this transformation where it's e to the power score divided by e to the power all the other scores, including this guy, and that's going to be a number between 0 to 1, and then actually get the loss, right? So that's the pictorial representation for feedforward network. And you can see that I can do, this transformation going from X's to H's. I can kind of repeat it multiple times. I can put another layer here. I don't have to call this a score. If I change instead of 3 as the W2's dimension, number of rows, maybe I make it 30. Okay, then it's again not fitting the number of classes that I have. So I have 30 outputs now. Let's call it the second hidden layers output, second activations. From there, 30, maybe I can go to 3. Okay, that would be a 2 hidden layer neural network. Okay, so one hidden layer neural network will have two sets of parameters, W1, B1, W2, B2. 2 hidden layer neural network would have 3 sets of parameters, and so on. Okay, so that's the representation. And actually, there's a you can go to this website, playground.tensorflow.org, and you can actually see you can change a lot of things. Here, it's saying no regularization, so you can set some L1 and L2 regularization, some coefficient multiplier for the regularization, which type of problem this is. Activations, you have the ReLU that we talked about and sigmoid, and there are a few other ones. For example, linear would be just what is it called? Multinomial logistic regression, multiclass logistic regression, right? And some learning rate, so I can reduce the hidden layers. Yeah, so this would be logistic regression. Okay, it's directly going from, it's directly going from inputs to a way to classify this data set. Okay, this data set, you see that it's not correctly classified, right? You add layers. Okay, I don't want to add 2 layers. And activation, let me choose ReLU. And you can already see, okay, what is the number of neurons? Yeah, so you can see how the number of neurons is affecting how it's being classified. So the way they are representing it as like any given point, what is the probability that it's in the orange class or the blue class? So it's still not capturing the, ideally you want to have a blue region here and everything else orange. but it's not yet, but at least it's not the line thing that we saw before, right? So maybe I can increase the, actually, you know what, I was not even training, so let me run the trainer. So now you can see this is what happens, you know, doing gradient descent. Okay. So actually, even before I should have trained with the multiclass logistic regression, but it wouldn't change much. You know, it will still be linear, so it can't really correctly classify. So you can play around with this to get an idea of what we discussed. Okay. Any questions? Yeah.
Which option is actually good? Increasing number of neurons in a hidden layer or increasing the number of hidden layers?
So these are all design decisions, right? So there is no good answer for either. As we just mentioned before, we are increasing the number of numbers, right? So now I have 2 matrices versus logic regression just had 6 numbers, the W matrix. Now I have 2 matrices with, if I choose the number of hidden units or hidden neurons to be, you know, 7 in this case, or whatever, 100 or 5, then you have too many numbers, right? That essentially kind of captures the capacity or some sort of a richness of that function going from input to output. Okay, so if you as you increase the number of hidden nodes as well as the layers, you are looking at more complex functions. Think of it as like if you decrease the number of hidden nodes and the number of hidden layers, think of it as like a function which can't wiggle too much. Okay, it's going to be somewhat of a linear, you know, maybe slightly curving and so on. The moment you increase the number of hidden nodes and the number of hidden layers, you can get all sorts of wiggly shapes, for example, in 1 dimension. And same thing in extensive multiple dimensions. Okay.
Essentially, if we increase the hidden layers too much, we might overfit as well.
Yes. Yeah. Good point. So if you increase, you know, you'll overfit, you'll get 0 training error basically, and that may not correspond to the, you know, the actual performance in test. Okay. So that was that. So let's actually go back to what we want to discuss now in the next 50 odd minutes. We're going to discuss convolutional neural networks. Okay, and for that we actually needed the pictorial diagram. So in terms of pictures, so we had an input which is a vector. In fact, it was 2 cross 1. Doesn't matter what is some dimension. We said it gets transformed to a vector which was, let's call it h, and this was x, right? It gets transformed from here to here. Let's say this is 5 cross 1 in a running example. But each node here, right, is affected by every part of the input. I mean, it's 2 cross 1, so only 2 numbers, but if it was 20 cross 1, then it would be 20 edges going to the first node only, and 20 edges going to the second node, 20 edges going to the third node, and so on, right? 5 nodes. So what I'm going to do now is that I'll just slightly change the picture. So let's say it was not 2 cross 1, but maybe it was let's say 25 cross 1. Okay, just increase the dimension. Okay, let's say I have 25 features. Then instead of this picture, what I'm going to do is I'm going to put those 25 numbers as a matrix. I'm going to do it as a 5 cross 5 matrix. I have 25 numbers. I can think of it as a vector. I put the numbers next to each other, 5 in one row. I get a matrix, right? So that's these numbers, right? I just change the input from a vector to a matrix, and then so I get to choose, you know, as you see, I mean, as you saw, I get to choose number of hidden nodes, right? So let me choose 9 as the, you know, I'm just choosing things which I can be made into squares. But let me choose 9. Okay, so let's say, so instead of h, this is instead of 5, it's 9. Okay, so that one again I can make it as a matrix, so 3 cross 3 matrix, right? This is in, whether it was 9 or 25 or even bigger, it doesn't matter. It could be 100 cross 100, for example. So now let's look at the first entry. It still is affected by every guy, right? So it's like a mesh coming out or going in from every cell of the input matrix. I'm taking, I have an edge, which essentially means there's a weight, a scalar weight, and I'm multiplying that with the inputs, the entries here, adding them together, and adding potentially a bias, and then taking the max of 0 comma that number, right? So just a different way to look at the same layers. It's still fully connected, right? It's looking at all the entries, right? Now I'm gonna do, so is this picture clear first? This should be crystal clear, and then we'll get to the next part. Anybody confused about this? Yeah, tell me. What's the confusion? I just changed the vectors to matrices. I just put them next to each other, huh?
How could you transform this into a matrix? I didn't understand that part.
So see, this was just a picture, right? So I didn't transform it. I'm just saying that in this picture, think of there's a bunch of 25 numbers here, right? I'm just saying that these 25 numbers contribute to the evaluation of the first hidden node's activation. Whether I put these 25 numbers in whichever way, whether I put them as square, in a square type of a representation or a vector type of representation, is the same. All there are 25 edges which go to the first number. So that's why I changed this to a square representation. Okay. I mean, this is just because I want to get to convolutions soon. But this transformation, there is should not be any ambiguity. There is no mathematical operation going on here. It's just a visualization that, okay, I had 25 numbers, I just changed it into 5 cross 5 numbers. It's just a visualization of that thing. Okay. And same thing with this hidden layer. Instead of 9 numbers, I just kind of shape it into a 3 cross 3 matrix type of representation. And so at this position, I want to make okay. I can actually generalize this, and generalization just means that I had 25 numbers. What if I had 50 numbers? Okay, 50 numbers are not a nice square, for example. So what I can do is, okay, I can put the numbers one behind the other, right? 25 numbers on the first surface or first matrix, and 25 numbers in another matrix. There's still all the edges are going to the first number. There's no change. It's just visualization. Okay, everything getting evaluated to all the numbers going to the first hidden node, right? Similarly for everything else. So you can see there's a lot of weights, a lot of numbers to be set. Okay, so that's one generalization. We'll get back to this pretty soon. But even with this single 25 cross 5 cross 5 matrix, what we're going to do now is do two things. Okay, first one is we're gonna drop some connections. Okay, what do I mean by that? So this thing which I highlighted here, the black, the activation, I'm not going to connect it to every one of the 25 and every one of the cells here. Okay, every one of the cells here. So remember, so the base case, this thing was connected to 25 previous 25 numbers before, right, in a square type of fashion. What I'm going to do is I'm going to drop some of the connections and say, okay, this thing is only connected to the first 9 topmost 9 numbers. Okay, so I'm going to say, instead of all connections, I'm only going to connect how many are there? 1 2 3 4 5, maybe one more. So I'm only going to look at these guys and only connect them. Okay, I just dropped a few connections, that's all. It's bad, but I dropped some connections. For the next guy, okay, this thing which I just put a small circle, I'll do the same. It was connected to everybody. I'm going to drop some connections, but not the same connections as the one next to me. So I'm going to drop a different set of connections. Okay, I'm going to retain the next 9 numbers. Okay, so basically the slightly shifted, but only those connections I'll maintain, everything else I'll drop. I'm just motivating towards why, I'm trying to trim, so convolutional neural networks essentially remove some redundancy, so they are more efficient in terms of parameters. So they have less numbers basically. So W matrix has lots of numbers. If you think of feedforward network, we had lots of numbers, right? By dropping connections, we are removing some weights, essentially some parameters. Lower, it's a smaller dimensional problem. Okay, so this is this is what I'm going to do for every node. So for the top guy, so topmost left guy, so let's say this is the top left. I said I'm going to look at only the first 9 numbers of that matrix. For the center guy, I'm going to look at the 9 numbers in that matrix but shifted. And for the next guy, I'm going to look at the 9 numbers in that matrix but shifted again. Okay. And in this, I chose 25 and 9 such that it nicely works out that the last guy, so this guy, looks at a 3 cross 3 which is at the boundary of that input. But let's not worry about it for now. Okay, let's do that for every entry now. Okay, so there are 9 numbers here, right? So this hidden node had 9 numbers. For each number, I'm only going to look at some sort of like it's called receptive field. Okay, it's a receptive field. That's the name, but it's just saying that don't look at this computation of the activation of this node. Don't connect to everything else. Just connect it to the things which are like in spatially are in some sort of sense close. Okay, spatial. I don't know if this is the correct word. Okay. And second thing I'm going to do is that, okay, so just again revisit this black thing. It was connected to 9 numbers, right? Let's call those 9 numbers. Let's give them a name. Okay, I'm gonna call those those not the 9 numbers but the edge weights. So the edges. So the edges were corresponding to some weights, right? I'm gonna give them special names. I'm gonna call them F11, F12, F13, F21, F22, F23, F31, F33, F32. Okay. Don't worry about the subscript 1. It's just there are 9 numbers, right? There were some weights. Remember these weights, these types of weights. I'm just calling them Fs. Okay. There are only 9 of them to evaluate the first guy, right? The black cell. I'm going to use the same numbers to evaluate the next guy. Okay, in the sense this dot, or let's call this across. Oh, now it's messy, but I'm going to use the same 9 numbers to represent to get the activation for the one next to it. I'm going to use the same 9 numbers to compute the activation for the next unit, which is this guy. Right? This guy. Same 9 numbers for this, same 9 numbers for this, same 9 numbers for this. So how many numbers do I have? Just 9, right? I went from a 25 dimensional input, right? 25 numbers, which was my input. I came to 9 numbers, 9 activations. I only use 9 numbers. Okay, these 9 numbers. Okay, so there's the spatial aspect that I said, and there's also reuse aspect. I'm using the same numbers. Okay, these set of 9 numbers are called a filter. Okay, just a special name. So what I'm trying to kind of move towards is that initially I had this W matrix, right, which was like a linear, which was in this type of a visual representation, right? Hidden layer nodes and input nodes. Now I just transform them into squares, basically hidden and inputs. Then I drop some connections so that I have this smaller receptive field. And then I also said I'm going to reuse the same 9 weights. These are weights parameters while computing the activation, right? So how would these 9 guys work? Because there are only 9 numbers in this input, so I'll multiply the first entry with the F11, second entry with the F12, third entry with the F13. Multiply it element wise, add them together, do a max with 0, that with potentially a bias, and if it is greater, then that's my H value for the first cell. Okay, that's the computation. Okay, so this is called a filter. Okay, there are only 9 numbers. I want to increase the numbers, so I can apply multiple filters. Okay, I can have multiple sets of 9 numbers. Okay, so let's think of 2 for now. Okay, so I have one set of 9 numbers. It produces this guy. Maybe so that's this. Let's call this F1. And similarly, let's say we have another F2 matrix, which is again 3 cross 3 dimensions. With that, I can produce another layer, okay, another layer which is again 3 cross 3 in this example, okay. So I'm saying that I can increase these sets of 9 numbers, I get more and more outputs here, activations, but these sets only operate on parts of the input, okay. Spatially, in fact, spatial is important, and I use the same 9 numbers as I move along to compute different entries of this 3 cross 3 matrix, okay. So this operation, so what is the operation happening? So let me draw a better picture. So right, so I had a filter F1, it gave me something like this, and I'll explicitly tell you what the numbers are. Let's say these numbers are 1, 2, 3, 4, 5, 6, 7, 8, 9, just to kind of ground everything, right? Let's say these are numbers. F1 is a matrix. Again, it's a, let's say for simplicity, F1 is just 1, 1, 1, 1, 1, 1, 1, 1, okay, simplicity. Then this first number is going to be just a sum of, I'm going to do what, I'm going to do element-wise multiplication of F1 with these guys, each of these numbers. So there's a sum to, so what is the sum? It's 90 by 2, maybe, n times n minus 1 by 2 or something. Is it 90 by 2? 45. Okay, so this is going to be 45, and you max it with 0 on that number, and it's still 45, okay. But you can imagine, numbers, some numbers may be negative in some other parts. So if they add them up, maybe it's less than 0. And if you do a max of that number and 0, then you get a 0. Maybe you got a 0 here. Here it's 45. Okay, that is it. That's the computation I'm saying. Here f did not change, but the numbers, maybe it's like minus 100 here. So the whole evaluation here, you came to a negative number, and max of that negative number and 0, you got a 0. Okay, that's the computation. And if I have another f2, I'll get another slice like this, okay. Let's say it's the same 3 cross 3, okay. So that's the explicit computation. Is this clear? At least the computation. We'll map it back to convolutional soon.
Do both the filters need to have same dimension?
Yeah, they need to be same dimension. I mean, in this architecture that I'm going to describe, which is the most vanilla or the simplest one, they have to be in the same dimension. So these matrices, we're just calling it as filters, okay. I can have as many filters as I want. If I have 10 filters, on the output side, I'll have 10 matrices next to each other, so it'll look like a tensor. Tensor is just like a 3D matrix, okay. It's like each slice of matrix stacked on top of one another, it's a tensor, okay. Like think of Numpy ND array, you can have more than 3 dimensions, and so it's like stack these matrices, okay. In this case, there are only 2 slices of 3 cross 3, okay. And so these are the parameters f1 and f2, which have, for example, 9 numbers in f1, 9 numbers in f2, total 18 numbers. Those are the only 18 numbers which are going from input to this tensor, right? So this operation is called convolutional layers operation. With ReLU, I just added a ReLU, but the operation before that, just to get pre-activations, is essentially element-wise multiplication of these f's with inputs, parts of the inputs, which I said the receptive field. In this case, the receptive field was just this. Yeah.
How do you fix the 9 numbers for a particular filter? Is completely random?
Great question. So these numbers are not fixed, and we need to learn these numbers. Just like in the feedforward neural network, we need to learn the weights. Here, we need to learn these numbers. So these 1, 1, 1s, we need to change. We need to change them such that the convolutional neural layer as well as the network itself can do better classification, prediction, and so on. So these numbers that I chose is just some sample numbers, and we need to kind of do a gradient update on these. So we need to change these numbers.
You mentioned special closeness earlier.
Special. Oh yeah, that's just to kind of contrast it with. We are going to reuse the numbers. So whatever the numbers are, in general, if let's call this f11, f12 that I used here, right? I'm just reusing them in the sense of when I compute the second. So I computed 45 here. right? I use the same bunch of numbers, whatever they are. In this case, 1, 1, 1, 1. Let's say there's a minus 100 here. In fact, let me actually compute it. Minus 100, maybe 0, 0, 0, 0, 0, 0, 0. Okay. For this part, okay, the last bottom 3, 3 cross 3, is going to determine this guy. Okay. So what do? You multiply 9 with 1. Everything else is cancels. Minus 100 with 1. So it's minus 91. Okay. Minus 91, max of minus 91 comma 0 is 0. That's why I put a 0 over there. But I use the same numbers. That's all. That's the reuse part of the matrix, of the filter. Spatial, just because I'm only looking at, the input was 5 cross 5, but I was only looking at 9 numbers in some, in a spatial sense. Which 9 numbers are, it requires positioning these matrices properly so that for the top right, so top left guy, it has to be the top left 9 numbers. For the bottom, bottom right guy, it has to be the bottom right 9 numbers, and so on. That's all. Any other question?
For both filters, we need to take the same input.
Yeah, so the filters are operating on the same. I mean, these numbers are fixed. I have 2 different filters. I get 2 different matrices. Yeah, and also remember that if I had, if I stack the input as 2 matrices, like this part, I'm talking about this part now. If I had stacked the input as 2 matrices, okay, then my filter cannot be just one matrix. It also has to have 2 matrices. Okay, right? I mean, you want to do. I'm looking at a spatial small part, but if it has two matrices, one behind the other, then my filter also should have same number of numbers. Essentially, the number of numbers in the filter has to be the same as that part that you're looking at. Okay, maybe that part has depth in the sense of like this, like the 50 numbers that I arranged 25, 25 as 2 matrices. But other than that, everything else is the same. Okay, so if the input has some depth, so think of this has some depth like a brick. Okay, if the input has a brick, then F1 and F2 will also be like a brick, look like bricks actually. Okay, you just do element wise multiplication, check whether the number is higher than 0 or not, and do appropriately plug the number out on the outside. Okay, and you get a flexibility on choosing any number of filters. Maybe I choose 1000 filters, then I'll have 1000 such matrices giving me as the output. Okay, I can just stack them together to get a 1000 depth tensor. Yeah.
The ones in the middle. So basically, this matrix is all the nodes, right? Oh, nodes in the hidden layer, right?
Which matrix?
The one in the middle.
Yeah. These are the activations. These are the activations. Yes.
How do you visualize these things? There are so many nodes repeated again.
Numbers are not repeated, right? Yeah, they are different. Yeah.
So after multiplying with F1, you're getting this node.
Yeah.
The second one, you're getting it by F2, right?
No. This one, this one by direct F1. These guys by F2.
Yeah.
All these guys by F2.
How do you visualize it in the neural network?
So you don't visualize the Fs at all. You don't visualize the F matrices at all. You don't. I mean, similarly, like if you saw the feedforward neural network, the Ws were not being visualized. They were just edges. What was being visualized was just the hidden layer node arrangement, right? And edge drawings. Here we don't explicitly draw the edges. I mean, if you draw the edge, it exactly like 9 arrows going to the first number, 9 arrows going to the next number, and so on. But we will not draw the edges generally. Actually, there's a picture, right? So where is my slides? Okay, I did not even start the slides, but let's see. Yeah. I don't know. How do you move forward? This doesn't work. Let's see. So this is what I just explained, right? Yeah, I mean, so this doesn't exactly get to that point where, so this was just a changing of the shape that initially, if I had a feed-forward network, then I can just change I can just rearrange the hidden nodes and the hidden nodes, right? So here there's multiple hidden layers, but just think of this part. Actually, like think of this. Oh, it doesn't write. Actually, oh, okay. I have it. Okay. I can't annotate right now, but it's fine. So if you look at this, this sorry, oh, this is 65. Oh, the answer to his question is 65. Oh, okay. No, I was just trying to say that for even feed-forward network, I just rearrange the inputs and outputs. So I said this node is kind of being impacted by all the entries. Okay, when I draw the representation, I'm just saying a part of this entry is being impacted, impacts or is being used as input to compute an entry. Okay, that was the spatial part, and the reuse part is we'll get to pretty soon, as he pointed out.
So now each layer will be a tensor.
Each layer will be
layer is a tensor.
Yeah, I mean, so we are gonna go from blocks to blocks essentially. Instead of, so think of, first understand that we can go from matrix to matrix. If we have one filter, if we have multiple filters on the output side, definitely we can have matrices stacked on top of each other. So that's why we get a tensor. But input can also be a tensor. If input had like 2 layers, then my filter would have 2 layers. That's all. So if the input is a tensor, it just determines the filter being a certain size. Actually, yeah, I think this is a good enough picture. So think of the input now as an image. Okay, so image has in this case the image has 32 cross 32 cross 3. Just means that 32 pixels, and then 3 just because RBG, for example. Okay, now let's say our output is actually is going to be for example, it can be the same size as the input. For example, let's say it's also 32 cross 32. I'll tell you what the filter size is needed, or what change is needed to have the same size. Let's not worry about that. Let's say the shape of the output is the same. So input was 32 cross 32. If I use one filter, then I'll get a 32 cross 32 matrix as the output. That's this guy. So this one neuron highlight. Okay, so I should use this. So this one neuron here, okay, is looking at a small part. That's the spatial part, and is getting computed. So there's a filter which is not being shown here that multiplies with this tensor block. Okay, it's let's say this is 3 cross 3 cross 3. Okay, 3 cross 3 in terms of spatial, and 3 because the depth is anyway already 3, and all that is element wise multiplied, maxed with 0 and in that number, and you get a value here. Okay, you can move the same filter around. Essentially, you can compute the same thing on a different block, maybe the top right corner or the top left corner, and so on. So you will get a slice. Okay, this slice over here would have all the numbers corresponding to that filter, and you can have, in this case I'm showing 5 filters, so 5 that's why I stacked 5 neurons, and just few of the neurons is what I'm showing, but the whole thing computed is a tensor. Yeah.
How do we decide which block of numbers will be used to calculate the number at the neuron?
Yes, so that's a good question, and that's the spatial aspect, which is best illustrated by looking at animation. So let's try this. Okay, so here's the input. So in this case there is no depth. Okay, it's a one layer matrix. So matrix is just grayscale thing. Okay, it's just a bunch of numbers between 0 to 255. Okay, that's the input. So the one on the left side, okay, don't worry about the animation, but this thing on the left side, this guy image, is the input. So think of one filter now. In particular, I'm just picking some number. Okay, I mean, you asked the question how these numbers are picked. We'll get to the way the filter entries are picked, but let's say the filter entries were exactly this. Okay, let's say. Okay, then I'm gonna look at the top, I guess top 9 numbers in this case. Can you see the cursor hovering on the 9 numbers and getting element wise multiplied in the center part? Okay, so the 9 numbers in this case were 206, 205, 247, and so on. They're getting multiplied element wise by 0, -1, 0, and so on, 3 cross 3. Ultimately the number is 65. Okay, and that number is highlighted in this red at the top of this guy. Okay, and then I can choose that maybe I'm gonna move exactly one step to the right. Okay, Okay, it's not one step to the right. Let's say one step to the right. I moved exactly one step to the right, right? I have same rows, but one column different. So I got a different. Sorry, this is 2. Okay, this is one step to the right. I hope it's not moving. Yeah, one step to the right. Previously, I got this number. Now I got this number. Okay, so depending on how many steps you move to the right, I mean, it's a nice, I would say, geometric structure. You cannot move arbitrarily. Literally, you have to move left or right, top, down. That's it, right? So if you move a little bit, if you take one step, then you can compute this number. You can also compute this number by saying, okay, I'm going to move 3 steps. That's also fine. You just use whatever pattern you want. Okay, how many steps you want to move to the left, how many steps you want to move down. You just fix the same pattern, repeat it till you reach the end of the image. Okay, till you reach the bottom right, and that's it. You'll get a bunch of numbers. In this case, they decided that they wanted to move one step to the right, get the second number, one step to the right, get the second number, and for the second row, move one step to the bottom, get this number, and so on. So they got this. Okay, what is this black border? Is because it's not the same size anymore. Because of the choice of steps, the outputs is not the same size as the input image, so they just added a black border, which means that 0 entries in that cell if they wanted to maintain the same dimension. Okay, but if you don't, you don't have to care about it. Okay, so that's the computation of a single filter. Okay, and these are hand designed filters. These are I mean, the terminology filter comes from I guess signal processing. So these are some hand design filters that people were using to detect edges in images, detect curvature in images, detect various things. I guess so to do some operations on images basically. Okay, so but you can actually learn these entries, and that's the whole point of convolutional neural networks, that you learn the entries of these filters by doing backpropagation. It's the same as before. Before you had the huge, single, nice idea of a single matrix, the W matrix, W1 or W2, or both of them. Here, instead of those matrices are replaced by now with filters. That's it. Bunch of filters. I mean, you get to choose how many filters you want. Okay, that's all. Yeah. Anything else here? Yeah. So there is some nomenclature, but let's not. I mean, you can check these nomenclatures. Stride means how many steps you move to the left, okay, to move to the right and so on. Zero padding is essentially the border. If you want to give some border zeros to your output tensor, you can give it. And layer depth corresponds to, if you use 5 filters, you'll get 5 matrices, right? So the depth of that output is going to be 5, right? I mean, the matrix itself in each layer could be whatever size, depending on how much you move spatially, right? So those are just names for the things. Yeah.
So this entire convolutional neural network makes sense only when that spatial element is actually relevant in this case. So in image, the pixels next to it are actually relevant for.
Yeah.
But in any other case where the features are not, the spatial representative features are not.
Yeah. Precisely. Very good point, actually. So there's this notion that we don't have to do any feature engineering and stuff with deep learning. We are actually doing feature engineering. Images have this spatial aspect, like images. For example, whether a cat is in the top left corner or the bottom left corner, it doesn't matter. There's translational invariance, for example. So there's positional invariance. Rotated image is the same thing. There is some spatial aspects, spatial structure, local aspect to that input data, in this case images, which is what we're exploiting by these filters. Okay, it's essentially filters are essentially picking up parts in the input image at the input layer. Of course, at the intermediate layers, it's not clear what they're picking up, but they're picking up local aspects of the problem, I would say. But it's not just images. For example, text also has spatial information. Okay, a word cannot appear randomly next to some other word, and there's some structure. Similarly, for time series data, there is spatial in the sense, input x, vector, there is relation between the numbers, order relationship between the numbers, for example. So for all those, you can use this type of an idea. Let's see. Yeah, so I guess this is a better picture. So that was the slice. So given that input 3 cross 32 cross 32 cross 3, I would use the same filter to compute that green slice, basically. Same, let's say 9 numbers to compute the green slice. Actually, yeah. And this is another example from this website where the input has, basically the 3 depth input, and I have a filter. The number of filter slices should also be the number of input slices. So input, for example, if it's an image, there's going to be 3. It will have 3 RGB parts, right? So let's say the input is actually 7 cross 7 cross 3 in this example. Then because the input has a depth of 3 matrices next to each other, filter will also have 3 slices, and each number at the output, this output, or let's pick this output, then this filter is looking at all 3 slices, doing element wise multiplication, adding all of them up, adding a bias, and then doing a, take a max of 0 comma that, for example. Okay, so you just get an idea of like what's happening at this really small scale with the example, and then that's pretty much convolution. Yeah, so that's what I was trying to illustrate here. Next, what's the time? Okay, we have very few minutes, so I'll illustrate another layer, which is a very simple layer. It doesn't have any parameters in the one in the simplest form. It's called the pooling layer. Okay. We are just going to call these things layers. So feedforward network, any the hidden activations, whether I put it vertically, let's call it a a generic layer, linear layer, let's say, and the convolutional layer, which gives me a tensor, let's call it convolutional layer, and pooling layer also does something. So for example, you should always imagine these things as like taking some rectangles, bricks, and giving us another set of cuboids of different shapes. Okay, so pretty much every layer does this. Maybe it's like elongated or something. So what does pooling layer do? It's a very simple operation. So let's think of a matrix. So let's pick a slice. Okay, let's pick a slice of this input data. Okay, it could be activations arranged in a certain way. It need not be all the way. It need not always be the original input. Okay. In particular, I'm going to pick it such that it's 8 cross 8 for simplicity. Again, just illustrate what pooling operation is. So let's say there are 4 numbers here. 4, 2, minus. Okay, minus cannot be there because I just did a ReLU. Let's say ReLU operation from the previous layer. And 1, let's say. So those are the 4 numbers, and there are 12 other numbers in this matrix. Okay. Oh, sorry, this is just 4 cross 4. Okay. So pooling just corresponds to some sort of averaging or some sort of reduction in information. Okay. Pooling pool just means like instead of maintaining 4 numbers, what I'm going to do in this particular case is I'm going to reduce these numbers to 1 number. Okay. In particular, there's this version max pool, just means that take the max of these 4 numbers and just that's the output. Okay. That's it. There's no parameters for this operation, right? I mean, it's a max of 4 numbers. Whatever the input was, take the max and that's the output. Okay. And similarly, you can have average. For example, you can just, I don't want to do max pool, I can take an average. So maybe you take the average of these 4 numbers, anything. So it's just reducing the information from, so I did it for 1 slice, I can do it for every slice like that. Okay. So that's it. That's pooling for you. What we're doing, what are we accomplishing with pooling is that, remember one use of pooling is that it's kind of reducing the number of parameters. Okay. Already by this notion of filters and the spatial restriction and reuse of filters and so on, we reduce the number of parameters quite a bit, right? Now on top of that, if we do pooling, we are reducing if the input was 4 cross 4 and let's say this depth was 12, then the output is not going to be this actually. It's going to be the same depth, okay? But it's going to be 2 cross 2 and this is going to be 12, let's say 12. Yeah. So it's just the same. I just reduced per slice. I just shrunk the matrix. Okay. So that's it. That's the pooling operation, and people do it only to kind of reduce the number of parameters. So if I have less numbers here, it's 1/2 the numbers of the 1/4 of the numbers that were there before, right? So if I connect a fully connected layer here, then I'll only have to have a matrix which is like whatever is output. Let's say these are already scores that I want to compute. Okay, let's say there are 3 scores. So 3 times 12 times 2 times 2. Okay, that would be the one dimension of this W matrix. But if I did not do max pool, then I'd have to 12 times 4 times 4, which is too many numbers. So it's just a choice that you can do, use to kind of reduce the numbers. Okay. So those are essentially the 2 key parts. So given that, here is an example CNN. Okay, just to kind of at a block diagram level. Yeah. So let's say the input is 32 cross 32 cross 3. Okay. So maybe I use 5 filters of 3 cross 3 3 cross 3 dimensions. 5 filters. Each filter will need to have a depth of 3 because input has a depth of 3. So I'll have a output. Because I use 5 filters, there will be 5 slices basically, right? 1 slice per filter. And I didn't tell you like what is the spatial stride and all that, like how many, like each cell here, how many neurons is it like looking at, so on. We can do that computation, but that's not very critical. So let's just say this is 12 cross 12 cross 5. Okay, that's this tensor. Okay, then I'm going to do max pool. I mean, pooling itself is clear. Max pool is just take the maximum number, right? So it's 12 cross 12. It becomes 6 cross 6. Okay, I don't have to really pool 4 numbers. I can always pool like max out of 9 numbers or max out of 2 numbers and all that. So there is a lot of choices there, but this will reduce the dimension of the width and height by 2, right? Because I'm max pooling 4 numbers. So 6 cross 6 cross let's say 5, and then I just do a fully connected linear layer. So let's say I call it linear layer. Okay, linear layer, let me just represent it as a vector. Okay, and let me just choose a number which is like 100. Okay, 100 on the output side. So we know what the matrix here. It's kind of clear. There's no notion of filter. It's just a W which has the output is 100 rows, and the number of columns is 5 times 6 times 6, right? And then maybe I really have to do 3 class classification. Okay, I need to produce 3 scores. Then there's another W, okay, which is related to this softmax operation, right? So that W will be 3 cross 100. Another W. This is an example of a convolutional neural network. And from scores you get to the loss, and then you backprop to update the W matrix. This one, you update this guy. There is no parameters here, and then there's 5 filters you update. Okay. So these are all the things that you update, the tick marked ones, so as to minimize the loss. Keep doing that by gradient descent or variations of that you'll see, and you try to classify as well as possible, minimizing the cross entropy loss. Okay, so that's an example of CNN. I think that was pretty much it, right? Let's see. Yeah, so that's pretty much it, except I want to see what is there. Okay, we saw feedforward network with backprop, that script, right? So we ran this, and we got for the 2-dimensional data, we at least got a really nice picture. This script, next script, it is actually from PyTorch tutorial. So it just shows you some data transformation things, which will actually be covered in the next lecture. But if you are adventurous enough, at least you should step through, put the data in the right directory, and run through the script, at least run through the notebook. Okay. So any questions about CNNs? This is it. This is demystified. Pretty much nothing. There's nothing else for the vanilla version. There are other ways, more exotic architectures which are different. But this is pretty much what the CNN is. Reducing the number of parameters by just looking at exploring the spatial aspect and this notion of filters. Okay, thank you.